It's good to be back. It's been a few years since I've been to a Zen Summit. I was at one about 5 years ago, and I found my old shirt from that time. Actually, I have it on. You don't see it there, but anyways. But the shirts have got much fancier. They're collared, and they're beautiful shirts now. It used to be just caps, I think. Wasn't that right, Ian? But anyway, so virtualization technology is expanding rapidly in both the server as well as the client environments. Let's briefly look at some trends that are currently driving this technology, discuss some of the future factors influencing virtualization. Then what I'd like to do is spend a fair amount of time on review of our AMD's next generation IMU hardware design. So today, virtualization provides the opportunity for a substantial cost improvements over a non-virtualized data center. And as companies strive to reduce expenses, the total cost of ownership of the data center is under very close scrutiny. And current servers on the average continue to be very underutilized. And they're still very ripe for transition and cost savings. A lot of the low-hanging fruit with some of the data centers where there's a clear transition, a clear cost savings to virtualized environment. Many of those are gone, but still, there's still lots of opportunity. Simplification of the data center management process is another key area driving improvements to the virtualization infrastructure. Dynamic provisioning of virtual machines, for example, allows a very easy and very rapid installation of additional workloads. While the traditional methods with static data centers can require a substantial amount of time to requisition new hardware, get that hardware installed in the data center, and the software up. So we've seen 5, 6, 7 months from when you order the equipment to approval to installation. Workload management improvements include load balancing capabilities, easier server maintenance, and reconfigurations are helping to drive improvements with the help of live migration of virtual machines. Now, live migration is a very, very powerful feature, and it's mostly a virtualization-centric feature. But overall, virtualization technology is very capable in its ability to provide a truly scalable multi-core workload environment. So it's maybe a bit of an eye chart with those charts on the right, but moving virtualization feature sets forward, it's a cooperative software and hardware effort. In the hardware area, CPU-specific trends are to assist with the actual overhead involved with virtualization. So 2 areas specifically relate to world switches, transitioning from a hypervisor to your virtual machine. So the first area is the actual reduction of the world switch times. And secondly, the frequency or the number of world switches that actually take place. So the chart in the lower right there shows originally world switch times were 1,400, 1,500, 1,600 cycles in the average. It's down to 600 or 700 or 800 cycles now. And these are just averages. Each VM exit takes a different amount of time. But in the future, we want to get this down to about the same level as a fault in the system. So we want to substantially reduce the time even more. The CPU is also changing to utilize better caching schemes for the guest state. And then we can utilize currently the tag TLB entries, reduces the number of TLB flushes, increasing performance. And then obviously reducing the number of world switches, the amount of world switches, can provide another level of performance improvement. Nested paging, for example, it's been around a while, but that can give us 10, 20, 30%. And in some specific workloads, certainly not all the time, but get us 70% performance improvement. But one area, IO virtualization, and Ian talked quite a bit about this, is an area of considerable interest currently. And one of the big examples is providing a direct device assignment to guests. Using the current IMU, hardware support can give us a distinct performance improvement. And then para-virtualization in the guest allows for the batching up of work, which can dramatically reduce the number of world switches. So what does the future look like? Can we predict the future? Well, obviously not. But the future's, everyone's probably seen this cartoon before. I love Dilbert. But the future's not really taking long to get here. With virtualization changes They're occurring very rapidly in both the software as well as the hardware environments. And these changes are not occurring only in the server space. As once again, as Ian showed earlier, the client space, well, Zen is clearly leading in the client space concerning virtualization currently. But with the polishing up of the platform virtualization capabilities, the x86 space is beginning to match, even exceed the mainframe or the enterprise space in terms of overall capabilities. So once again, the IMMU supporting our virtualization is just one example that allows virtualization support to help x86-based machines to not only match but exceed the enterprise class machines. And so these advantages will help move even more data centers either partially or completely over to a virtualized configuration. So also the uses of virtualization are expanding rapidly. In order for virtualization to get even or grab even more share of the data center, there are key areas of support that are more robust in the mainframe area need to be addressed in the virtualization arena. A virtualized data center needs to have or better security, quality of service, high availability, ease of manageability that's currently expected in the non-virtualized data center. So one distinct advantage that virtualization does have, and a key component, is the ability to manage workloads using live migration. But a fully seamless live migration requires a robust I/O virtualization support. So a big challenge has and is currently ensuring that a migrated virtual machine can successfully access equivalent I/O devices as efficiently as before the migration. And as such, there's been a distinct trend towards changes to support I/O virtualization. For example, smart NIC adapters with single-root, multi-root I/O virtualization. In the platform hardware, once again, I/O MMU is becoming prevalent in both the server as well as the client boxes. And then the software stack continues to evolve along with these other changes. So what additional support is coming down? What else can we expect with virtualization? Well, there's going to be some small changes, some additional acceleration modifications in the hardware. For example, virtualized interrupt controller to be able to reduce the overhead of inter-processor interrupts. Reliability, availability, serviceability must be improved. An example, when you consolidate down from, I've seen examples of 30 servers down to, say, 5 servers. When you have only 5 servers, if one of those servers fails, it can make a huge impact on the operation of your data center. And detecting hardware failures, for example, before they happen, is much more important in a consolidated environment. Improvements in VM failovers are expected. Ian had some information about that. A failover with a single core, for example, is much easier than an SCP guest with multiple virtual CPUs. We're seeing a wider proliferation of nested virtualization, especially, once again, as Ian showed in the embedded space, with a much larger base predicted in the future. So that's an area that's definitely going to expand. But virtualization where devices, it's a key area. I/O virtualization will be very important going forward. The standards are improving, single and multi-root IOV, address translation service specification, ATS 1.0 specification, now the 1.1 specification that supports page request index, or essentially I/O faults for peripheral devices, can be used with smart NICs, smart storage adapters. So with I/O virtualization clearly a big part of the future, how is the hardware providing additional assistance? Many of you are familiar with IMMU. We're just going to go over briefly. This is a very high-level chart here. We'll call this version 1. IMMU is targeted at both client as well as server. So an MMU provides translations between virtual addresses and I'll call them system physical addresses for the CPU, and IMMU does the same thing mostly for devices, converting device addresses in a virtual environment. This is a physical address to a system physical address for access. Both of these provide a level of protection, domain protection also. So let's take a closer look at an AMU configuration. So on the left-hand side, we have some CPUs with some associated RAM, a high-speed bus. On the right-hand side, we have some smart peripherals on the PCIe bus. In the middle, we have some bridge chips with AMU devices. So an AMU has right now a single level of page walker for translation. And the ATS 1.0 specification outlines a protocol to provide translation services from a translation agent, in this case, the AMU. So the optional ATC in the device, address translation cache, also can be called an IOTLB, requests of the AMU translations. And in this particular instance, would request a virtual environment, a guest physical address translated to a system physical address. So we'll go into a more specific example in a couple of slides here. So let's look at some of the uses for V1. As we've discussed, the direct device assignment to a guest, reducing the device overhead, IO virtualization. Many legacy devices require the use of low memory addresses. The IMU can seamlessly translate between these lower addresses and upper memory, helps avoid memory copies or bounce buffers. ATS 1.0 translation services, as we discussed, for devices that do support ATS. There's NIC cards that are coming out. I think there might be a few even being sold now, but it's going to be more prevalent in the future. Devices that support single root IO virtualization can also utilize, these virtual functions can utilize the IMU features. Device containment of DMA accesses that originate from a defined guest domain, specifically assigned to a guest. The DOS attacks can be minimized. Interrupt routing table can be utilized to make sure that you avoid issues with your hypervisor. The guest may get a lot of interrupts, but you're going to avoid bringing down the entire system. So the IMU definitely helps with IO virtualization, but what are some of the current limitations? Well, there's a new specification. Some of you may have seen this, an ATS 1.1 specification, Address Translation Services, that provides PRI, or Page Request Index, support. Essentially, this allows demand paging for a peripheral device. So without this feature, V1 in this case, provides no services for memory overcommit, no demand paging, essentially no I/O page faults. And then with only one level of page walking supported, these entries are not compatible with the OS usage page tables between the IMU and hardware. Without a second level of walking, there's no support for guest user level device assignment. So you have to use a guest physical address. You cannot use a virtual address. And the nested hypervisors, there's a lot of excitement around those. Those could use another level of translation. So given these limitations, what makes sense? What's going to come next? So we're introducing the next generation of AMD's IMU. So first of all, it's V1 compatible, 100%. With ATS 1.1 PRI support, we now support IO page faults for peripheral devices that do support ATS 1.1. This allows for demand paging, memory overcommit. Additionally, remote DMA can access now unpinned memory and doesn't have to only access pinned memory. There's a second nested level of page walking supported. We'll call this L1. This L1 allows us to go between guest virtual and guest physical translation. This level is 100% compatible with the current x86 64-bit page table format. What this allows then is the sharing between the IMU hardware and the guest page tables directly. This allows for the direct device assignment to guest applications. So now we can use a guest virtual address from the VM, using the peripheral, and can be translated. And then in a native environment, you can assign user-level I/O to devices. So since L1 can be shared, you're able to just point to that page table set and share the page tables for user-level I/O in a native environment. Let's see. So let's look a little bit about ATS. ATS 1.0 is pretty simple. In this example, the hypervisor has set up a set of page tables that map the physical memory that the device will be accessing. The device has an ATC to request translations for device addresses, which in this case is a physical address. So the ATC requests a translation from the IMMU via ATS over the PCIe bus. The IMMU looks in its local IOTLB, and if there's a miss, then the IMMU will walk a single level of page table to find the translation. So with ATS 1.0, you must return a translation. It's not really an option to fail this, as the device will typically go into an error state. So the page tables and the memory associated must be pinned in this specific scenario. So with V2, I'm on V2 with ATS 1.1 support, the PRI support, we can now support page request support request to page in physical memory. So once again, the peripheral issues an ATS to request a translation. The IMMU hardware looks for a translation, it's IOTLB. If not present, it walks either one or two levels of page table. If there's a miss now, the IMMU hardware can return essentially what's a page not present to the device. So the device then can issue, this is a new command with ATS 1.1, a PRI request. This is a request to mark that page, bring it into memory and mark that page as present. So the IMMU receives the PRI request and then places a command onto a new command log, the PPR, Page Peripheral Request Log, and interrupts the software. So in this example, we can be in a native environment and we'll call it a software driver. So the IMMU device driver then reads from the PPR log this entry. And it can interface with the OS memory management services to make that page present and to properly set up the page tables. The IMMU software then, once this is done, places a completion response onto the command queue and informs the IMMU hardware. The V2 hardware then reads the completion command and issues a PRI response back to the device. At this point, then, the device can reissue the ATS request, and the IOMMU hardware would then be able to return a valid translation for this newly present page. So essentially what we have now is we have the ability to perform I/O page faults for peripheral devices. So let's take a little bit closer look. If you can see that, there's a green area on the diagram here, which is the V2 portions. So in the middle we have the I/O page tables. With V1 we just have host translation. There's only one level of walking. And then with V2 we have host translation, but also guest translation. So GCR3 up there is the guest CR3. Those page tables can be shared. They can be in the guest and shared and walked by the IMMU hardware directly. On the right, we have the PPR log, or the page service request log, for PRI requests from peripherals. And then on the top, we have some new RAS hardware counters, some error registers up there. And then the others, V1 stuff, interrupt routing table, and some other event log and command buffers that are associated with V1. So here's a simple use case. So remote DMA, essentially RDMA-based infrastructures currently require pin memory. So we talked about this before, but a smart NIC that supports ATS 1.1 PRI along with an IMMU can then essentially support unpinned memory for its communication buffers and gives us a better, more advanced memory model. V2 can also provide direct mapping from user level on the guest to a peripheral device. So we've already talked about this somewhat, but essentially you can go from a guest virtual address to a guest physical and the L1 walking level, and then go from a guest physical to system physical. So you can use guest virtual addresses, the same virtual address in the guest, as well as manipulated by the peripheral device. So virtualization is and will be even more so a critical part of the data center for the future. But it's also clearly an important part of the client space. So at the end of 2010, the prediction is that over half of the data centers will have some form of virtualization. And IO virtualization is clearly an integral part, an important part of the next generation of servers and clients. And here we have the next generation AMD IMMU provides another level of IO virtualization functionality, supporting demand paging, and helping with the overhead of virtual machine IO by providing a direct, secure connection between guest processes and peripheral devices. So I just love this picture. It's like virtualization exposed. But not sure. We're almost on time again, aren't we? But well, one more point. So the specification isn't quite out yet. It's always documentation. But in theory, it's going to be out this week. But if it's not this week, then we're going to publish it next week. And of course, not next week. Then it'll be the week after. But that's how it goes. But we're cleaning up some of the verbiage and English in there. But it's a pretty long spec. But anyway, the spec is coming out soon. You guys all be able to take a look at it and give us some feedback and let us know what you think. But I/O page faults and peripherals to me kind of exciting. But we'll see.
This isn't working right.
Can we borrow this one?
Speak loud. We have time for about 1 or 2 questions, and please speak up, and maybe the speaker can
Repeat the question.
Repeat it. Thank you. Any questions? Okay, go ahead.
So in the new scheme, after the I/O page fault has been satisfied, isn't the second lookup superfluous? Why is it implemented that way?
Make sure I understand the question. Let me go back to that diagram here, if I can.
Right.
So
Why the second ATS request?
So it doesn't have to do the ATS request again, right? So my first thought was, isn't that superfluous? So I asked the same thing, and the answer I got back was, well, no, because you may not want to do that ATS request. Maybe things have happened in the peripheral where, in theory, you're doing, say, speculative read-ahead or something. So you're just going to send a PRI request to read these pages in. You may not need that translation now. So, but it made sense to me when I first said, well, why can't you just give that translation back? But there's some reasons for that.
Okay.
Another question, yes. No, it's you, I think. Did you raise your hand?
Yeah, and why the emphasis on avoiding pinning memory?
So yeah, if you pin memory, it's more efficient, right? I mean, it's not like, you talk to people and they say, oh, you can now don't pin memory. It's what a better efficient system. It's not. That's not true. But it just gives us a more advanced memory model. So what you'll be able to do then is do demand paging and just use your memory more efficiently is what we're looking at here. So I'll ask the others, anything else? No?
Let you overcommit things to.
Yeah, overcommit, right.
Just a quick question. What is the timeline? When is this going to come in the product?
So we're here now. Oh, repeat the question, sorry. Yeah, so when is the V2 going to be out? We're here now. It's going to be somewhere in the future. I asked specifically about that question, and everyone above me said, you can't say that yet. So you knew that, though, I guess. Okay, any other questions that we have? Like I said, the spec's coming out, so it's a great read. It's almost 300 pages or something. I don't know how long it is, but truly enjoyable. It really is. Lots of great diagrams and everything in there. So.
Any other questions? Okay.
Yes.
You mentioned GPU virtualizations. Any details on that? Any types of cards that you're going to support in the future? Any details at all?
Yeah, so GPU, virtualization in the future. Yeah, clearly you could have any peripheral associated with, with utilizing the ATS window at one support. So GPU could be in the same realm. I guess what I'd say here.
Let's thank our speaker.
Oh, thank you.